Yeah, today I'm going to present about like our recent work, which is multilingual rubric agnostic reasoning reward reasoning models. Um, Essentially, it's just like a reward model that kind of like operates using rubric, and then it can take multiple languages and then also output like multilingual terms. Um, anyway, so maybe I'll start with like a brief introduction first. So essentially, we need to align LM behavior with like human preferences. And then if we try to directly collect like human judgments immediately, like basically asking people to compare outputs or rate outputs every time, it doesn't really scale well and it's kind of like expensive. Alternatively, which is what recently people do, which is using reward models so that like the model can rate like which response are better or even like rate it from like scale 1 to 5 or something like that, so that like the model can learn which one is like more desirable or preferred in terms of like the output. So it's kind of like cheaper in a sense, so that you don't have to ask human every time. But the current reward model have like some issues. So the first issue is controllability. So for example, like if you have like ARM or UniFL or some like generic reward model, they only support evaluating models on specific aspects. Let's say I can only rate this based on helpfulness or maybe safety. But it's not really like, let's say if you want to book a flight and then how you want to rate how good is the plan is, then it's a bit difficult to rate that. And then in terms of like interpretability, the scores generated by reward model can be difficult to interpret. So let's say like 0.6543, something like that, or with typical reward model it's a bit difficult to understand like is it like very uh way better compared to like 0.75 or something like that. And then like again with the controllability, is it a combination of helpfulness and coherence, or what are like the combinations? It's a bit hard to understand. And then in terms of like compatibility with like various tasks, um, they are mostly either only evaluating under point wise, so basically like scoring 1 to 5, or they're completely like a pairwise RM. So for example, like RM R1, they only compare like between response one and response two, which one is better. And finally, most of the works are English centric. So whenever you have like a multilingual input, then it's kind of becomes unclear because they are mostly trained on under English. So basically, this is a summary of our work. First, we have like basically kind of like an instruction, and then essentially to use like our model or our framework, you just need to provide some rubrics that you want to define. Like for example, here you define based on like pairwise kind of thing, where how do you say assistant B is better? Let's say if you want to say it based on like appropriateness, helpfulness in some order, or and then here are basically like the translation across like different input. So whichever language you want, we can like take that and then um, you give like the input of to compare like response one and response two. And then we can basically, because here you're specifying the rubric in terms of like pairwise, so it will just compare between like response one and response two. But let's say you want to give like you define a rubric where it needs to rate one response, then it will automatically like decide that like, okay, I need to rate them from 1 to 5, and then it will just go here. Or if you just want to see whether the response is true or false, like say in like RLVR scenario, then you can just go here and then where it just rates true or false. So, and then we have like multiple ways, whether you want to reason in English or Korean, you just need to specify it. Um, like reasoning here, basically like the internal reasoning. So not necessarily like the explanation, but the explanation will also be like in other language. But yeah, it's kind of like customizable depending on needed. Wait, okay. So perhaps I'll start with like the how do we kind of like train this overall. So first, I think to keep in mind like the goal of like our evaluation model is to give a high quality response according to human rubric, defined rubric. Um, that finally like produce a final score and then some natural language explanation for interpretability. Because let's say, we have like a score of 5, and then why does the score is 5? It's something that like we're looking for in terms of like generative reward model. So the main idea, since that we want to get like the model to learn different rubrics, is that like we have to diverse domains and then different task formats, as I mentioned, along with like diverse evaluation rubrics and explanation traces. And this is just a formal definition, but like essentially, it will be something like this, where you just take like rubrics, instruction, and then the inputs, and then finally like it will give like score depending on what kind of like input that you define, um, and also the language that you define. So I guess this is a comparison with like other works. Um, we trained across like 72 languages with only like 100K data set. Um, and then our model size is around like 4B, 8B, and 14B. Um, but like whichever to pick. And then we kind of like support like different kind of like formats. And then of course we open source it so that like people can use them. Um, so for example, if you look at like other popular work like RMR1, they're only supporting like pairwise, so it's a bit difficult. Let's say if you want to give like a score of a response with like a pointwise like. Um, and in terms of like the data set, the way we try to construct it is quite intuitive. So first, we try to distill like from teacher model, like what kind of like reasoning should be done with given like a certain rubric. Um, and then we just basically sample like if it's all correct, then we use them. So basically we have like a different kind of like instructions here and also like reasoning. So we try to ask the two reasoning in English, reasoning in like target language. And then we also try to vary like the prompt itself, like whether like the prompt should be like in English or like target language. And then finally, if all samples are correct, we just feed it to like the training sample. And then we also try to discard like easy samples. So for example, if we try to generate with like with this model that we want to train, like a small model, if we try to sample it like multiple times and it keeps getting correct, then probably it's too easy. Then it's not really useful to train it. Probably it's the task of like giving the score is like too straightforward. So we just discard them because it's not really helpful to train. And then yeah, it's also like mostly for efficiency. And the final data set is technically like 100K, as I mentioned. Um, and then in terms of like the training itself, how do we like train the model? We use SFT, and then we use like different base models just to see like how it's going on. I think later I will show like why here SFT is kind of better compared to like the other training paradigms that we try to explore. Um, but essentially, the reason for now, the intuition is that like you want to kind of have the model to mimic in terms of like rubric reasoning, and then it also like encourage to follow the proper reasoning that we have here. We use like the OSS 120p as like the generation. Um, and I'll go briefly to the results. So here are like comparison with like base models and like existing reward models and like our models. So even like with our models here, we are benchmarking across like typical reward modeling scenario where you rate like whether which one is preferred, like either in like multilingual setting like reward bench or MMEval or IndoPref, which is another reward bench of benchmark specifically for Indonesian. So yeah, I mean the performance here looks great, where we kind of like better in terms of like multilingual, even like sometimes better than like the original teacher model here. Um, Actually most of them. Um, but yeah, and then we don't really digress in terms of like English specifically in here. As you can see, like we can like maintain some performance, and like improve as well from like the base model itself. Um, and then if you compare to like other works which are like larger model, like here, for example, Nemotron like 49 billion, we kind of like surpass that as well, even with like a smaller model here. Um, and then we also try to evaluate like the knowledge of the reward model in terms of like here it's like more kind of like a general cultural knowledge, and then this is more like a math questions, and then this is more like a safety. We are kind of like doing well as well, slightly behind compared to like the GPT OSS 120p. But overall we can like maintain some kind of like knowledge, and then like can give rating depending on like needed. Um, and then we also try to investigate like what because this is a multilingual model, so maybe which one is like better in terms of like prompting in English or thinking in English since we train it like differently. Um, so uh, of course like the training with English full set seems to be better probably because like they also have a quite pre-trained knowledge using English in the first place, rather than like in target language, but it doesn't mean that the target language itself is kind of like lacking. So for example, if we compare it like base model, if you try to force it to think in like target language, it drops like in the terms of like a base model here. Well, once we train it with like our paradigm, it kind of like improves. So technically, oh, and also like it improves even better than like the original English base model. Um, like if you prompt with English and then think with English. It just means that like our training kind of like effectively improves like the multilingual reasoning quality, and also like the multilingual output of that. In hopes that like it's also interpretable. Let's say if someone who's not speaking English tries to understand what's the reasoning behind it, and then also like the explanation of that, of the different responses when giving a reward. And we also do some kind of like ablations. So for example, here, if we use like our reward model to well, this is like a off policy. We kind of like can show like we have like a better win rate, even like compared to like GPT-4 and Mini in this case. And then we also like compare like the improvements of the model when it comes to like different benchmark or like a multilingual reasoning benchmarks. So in a sense that like we kind of improve the reasoning capability of like the original base model here. Um, and then we also try to do ablation on like different data size. So as you go like as you go in terms of like scale of like 100K, the improvement kind of like gets better and better. Probably because we deal with like a lot of languages, so more data is needed. But of course, if we scale more than like 100K, probably the performance is better. But we just set to 100K as our budget at the moment. Um, and then another to point out is that like maybe there's like a maybe there's like a stigma like should we use like RL to train this like because like other reward model strategy they're trained using like RLVR, so that like it can learn more better and generalize better, but at least in our budget here, um so using RL actually using like the 50K checkpoint from here and then like train the rest with like RL is not really helpful. And then if we use RL fully from the beginning, it's also not helpful. It's even way worse. So we only kind of like report in terms of like the 50K and then like 50K RLVR, which is like typical. You do SFT first and then RL. Um, it seems like it's only better in terms of like safety compared to like the rest is kind of like dropping, possibly because um like with RL and then with this kind of like complex reward scenario, it's maybe like a bit more difficult to kind of like um learn better. And we also use like a strong teacher model as well, in a sense that like the model just needs to follow like a proper reasoning in terms of like rubric, and then it can basically give like a better signal. And then we also do ablation in terms of like curriculum, like which one that we did. There are some differences, but essentially we try to like do it different ways and then use that as part of like our experiments. I think this is more reporting like if you're curious about like the benchmark. But here we use like the validation set to decide what is our like our final curriculum. Um, um, and finally, we also do like human annotations because I believe this is more important because we claim that like our reward model is more interpretable. But how can we like ensure that if we don't really do any uh, human study analysis? So we recruited 20 annotators who are like native speakers from 12 different languages. One of them like including low resource and also like unseen to the training data, such as like Javanese, and then we also rate like Albanian and Telugu. So those are not really in our training set, but we hire those annotators to see whether their reasonings are good or not, since we also evaluate on like out of distribution scenario, even in like our benchmark. Um, and the way that we try to form the annotations is that like we try to understand whether the rubric itself is high quality or not, because the rubric itself is generated by models, right? And then this in summary, annotators find that like the quality of the rubrics is quite well. Basically, we have like some metrics to do it, like in terms of like plausibility of the scoring and then scorability and like the translation, whether it's good or not. But overall, they seem to be happy with that. Um, and then in terms of like the human evaluations of the training data reasoning trace, because we generate the reasoning trace from the training, and then we want to see whether like the quality of the training data is good or not. Well, I think this is not really unexpected because um, well, the GPT-OSS is better in like English, but like when it comes to like target language reasoning, it's kind of like slightly lower in coherence and factuality, which is kind of like expected, since the model is mostly trained on English. Um, so definitely, if we have like a higher quality of like reasoning trace in multilingual, then maybe it can improve better in terms of like the multilingual reasoning and like output. And then finally, we also have like human evaluations of like our model. So they find that like after training, our reward model is actually like more coherent and fluent. And they also mentioned culturally aligned reasoning because sometimes the benchmark can ask more about like cultural questions than like the original model. And then for some reason, even though like the performance kind of drops for like target language reasoning in like the final benchmark, um, but they prefer annotations with like target language reasoning. So perhaps it's sort of like this kind of like improved, I mean, multilinguality performance is actually more preferable in terms of like uh, preference in terms of nuance and cultural appropriateness, which means that like the study will be important, especially when people want to understand better about like reasoning in other language. And yeah, I think that's all. Like the conclusion is that like yeah, we have like a reward model. It's like multilingual. And then even like on unseen low resource languages, the annotator seems to be happy with the reasoning and also like the performance benchmark, they're happy with it. And then yeah, annotators prefer our reward model compared to like other reward models as well, including the languages that are not seen. Um, and then that's all. And then like if you want to check out like the paper in detail or like let's say check out the models or even like the code, I provide like the QR links here.
Thank you so much. Um, s- so, if there's any question from the audience or maybe the paired speaker evening, if you also have some questions to lead the discussion, that would be great. Um, Otherwise, we also have participants here. So if there's any question from the audiences, you can also go ahead with the chats on Slack or maybe the Q&A button on the bottom of this Zoom view.
Yeah, of course. Let's hear from the audience first.
Mhm.
Or I will ask for things. Um, so thanks Sarah for the amazing talk. And there are like three things I would like to ask. The first one is about the rubric in the framework. So you mentioned that the annotators also judge the quality of the rubrics, right? So is there any specific uh, format for the rubric in this training pipeline, or so like uh, do you follow a certain specific format or specifications to design the rubric for training and to engage in reasoning?
Oh, in terms of like the format of the rubric, we kind of like
Mm-hmm.
have like a template of like how the rubric would be. So for example, if it's like rating like pairwise, then it would be like, okay, you have to provide like description of like what is preferred compared to like another. And then if let's say if it's like a point wise, what is like the description of like 1 to 5 or 1 to 7 or anything that you want to describe. And then in terms
Mm-hmm.
of like binary, like what are the criterion of like a one and what is a zero, something like that. So
Mm-hmm.
essentially, that's like what's being rated by the annotators, whether the scoring makes sense. For example, if like say you have like a 1 to like 100, it's a bit difficult to even as a human to rate 1 to 100 is a bit difficult. But maybe like 1 to 5 is more like better in terms of like scoreability. And then in terms
Mm-hmm.
of like how different is like 1 to 2, 2 to 3, because like if it's quite ambiguous, then it's a bit hard to rate. So basically, those are like the what are being created by the annotators as well.
I see. So the model MR3 just basically follow instruction written in the rubric for different kind of reading.
Yeah, yeah. Essentially,
Okay,
the idea is that like the models itself will try to follow the defined rubrics, and then with that, it can give like a proper rating based on that.
I see. All right. And for the second and third are around the mean figure two, I think.
Mm, this one?
No, the one with the English and target language and like how you step training. Yeah, that's one.
Ah,
Yeah.
okay.
Uh,
Um,
so for non-English target language, do you also require an English pair that's the same task written in different languages?
so for this one, we don't really so, for this part, right? Like the initial
Mm-hmm. Yeah,
training, it's basically we want to compare like which strategy for training is better. Like, should we use like fully English prompt and English thinking, or what if we
mm-hmm.
just want to train with like target prompt and target thinking? And then
Mostly.
essentially,
I see.
like we try to provide a study where like everything like is always equal, so that like the
Mm-hmm.
only difference then when we want to train is only like the language itself.
I see. I see. Yeah, and on the second part, um, basically, you only accept the samples that are hard, right?
Mm, that
So
are
if
not too easy, I guess.
they are not easy. Okay. So I wonder if this choice cause any problem in like using the remote model for like IO training or stuff, because if all the incoming tasks are hard, I wonder if there's a difficulty in starting to give a useful reward for reinforcement.
Oh, sorry. Here it's just that like if it's too easy, but not necessarily like too hard. So, for example, like if the model can, let's say, answer 4 out of times, out of like 5, then like we still accept the sample. But if let's say if we sample it like 5 times, it keeps answering correctly, then probably it's not really beneficial
I
in
see.
terms of
So
like the
it's just
training.
not too easy and not too hard, just moderate difficulty.
Yeah,
I
exactly.
see. Thank you. Yeah, I think that's all from me.
Oh, thank you.
Good. And I think it's time to switch the roles, right?
I
So,
think there's a hand raised in the audience.
Oh,
that's good to know. Oh, that was. Yes. I'll allow Mayank to talk. It's good to see you again.
Yep. Hi, folks. For the previous speaker, I had a query regarding the metrics. So they haven't uh, s- shown any metrics that were relevant on the slides. So I was wondering, maybe if they could uh, delve deeper into that part.
Um, could you specify a metric that you mentioned, like which one?
Okay. So this is the slide. So this is like with respect to the accuracy of 18 languages versus 23 languages versus one language on different M reward bench, and MM eval. Okay. Okay, so I was wondering, did you also calculate like the uh, dependency of how it took, uh, since you have shown on the left the uh, base models and the reward models. Uh, did you also weigh in some other techniques to calculate the same, or like this is the only table that you have?
So essentially, there are like two flavor of benchmark that we have. So the first
Uh,
one is like traditional, like pairwise. The other one is more like kind of like scoring, like whether it's safe or not, like here, like 0 to 1. And this one is like more rating, like whether the explanation of like the math reasoning, sorry, the final answer of the math is correct or not. And this one is like more on general knowledge. Um, because I think in the first place, like in terms of like reward model itself, we are trying to predict, right, like what kind of like score makes sense in the final output. So that's why like the metrics are mostly like accuracy or F1 or anything like that. I don't know if that clarifies.
Okay, so you're able to detect like when you're going from one language to the next, or like in the mid sentence when you're like in a downstream task when you're trying to switch a language in the middle of a sentence. Is it able to deduce that, or like have some sort of uh, a, a kind of metric there?
Oh, sorry, I'm not sure what you mean by like switching language.
Like suppose you're talking in English and you switch to Spanish in the middle of a sentence for like three or four words. Is it able to deduce that, or like able to,
Oh, I
yeah.
see. In terms of like code switching, there's no benchmark yet in terms of like preference of on that. So I think that's something that like we try to explore later, possibly like in the future, because if there's no benchmark yet, then it's a bit difficult to understand whether we can handle code switching scenarios. But I think it's kind of
Mhm.
like interesting to see what will be like the case. But actually, in terms of like the reasoning itself, we can see a lot of code switching. Not a lot of code switching, but sometimes we see code switching in terms of like the reasoning of the model. But I don't know if it's because like it's more natural or something like that. It's kind of hard to say. Um,
Mhm.
but in terms of like the benchmark itself, we don't really test on like code switching scenarios.
Oh, okay, cool. Thanks. Good to know.
Yeah.
So thanks for the question. And I guess we need to switch now to have more time for the second speaker.
All right. Let me share the screen. All right. Yeah, am I sharing?
I can see your screen.
Sure. Turn on. All right. So, hello everyone. My name is Ethan, and I'm currently a PhD student in UC Davis. And my main research focuses on helping AI to understand programs, and so helping AI for software engineering and software security. Okay. So today, I'm presenting our work in evaluating program semantics reasoning with type inference in System F. And this paper was published in Neuroips this year, and just reusing the slides. Yeah, let's get started, right? So I will start with some background on reasoning in large language models. So basically, the current paradigm is for text and computers. Let's think step by step. They started from 2022 with the chain of thought prompting, which enables reasoning in large language models. And then COT, which stands for chain of thoughts, is decomposing multi-step problems into a bunch of intermediate reasoning steps to help the large language model give a better answer. Right? And after that, COT has become a training paradigm from like OpenAI, DeepSeek, and all the model released recently. Right? So we have an example of a test on computer reasoning in Figure 1. I took it from the S1 paper. So basically, it's counting how many letter R's in the word raspberry. You can see that the reasoning trees is decoupling the question answering into multiple intermediate steps, and finally deduce the final answer. The final answer is that there are 3 R's in the word raspberry. So as a related example, we can view this kind of reasoning steps as the steps on the right. So we have a large language model with pre-trained knowledge. Those are the learned rules. And we have the prompt and in-context knowledge that are the assumptions and hypotheses. If we can view the COT steps, the reasoning steps, as a bunch of lemma 1, lemma 2 given during the reasoning, we can finally reach a response, which is a proposition. So, however, there's currently a evaluation gap for reasoning models math and code. So, for example, for mathematical reasoning, there are a few very famous benchmarks that are used all over the technical reports or the papers. Those are AMI 2024 and Math 500. Those are high school level math computations and problem solving. And for code generation, we usually use Left Code Bench that are coding context problems, and SweetBench that's for generating a patch for resolving issues on GitHub, right? But what we think is that the idea of real reasoning, the logical reasoning for code, and that's why we want a program-centric deductive system that is purely focused on reasoning about the structural logic behind the programs, instead of like generating a patch or generating script to resolve a problem. All right. Let's first briefly recall the definition of a formal reasoning system or a formal deductive system. Okay. From philosophy or mathematics, we call a deductive system. It's a system specified by first a collection of judgments or assertions or validations, and second, a collection of steps or aka the inference rules that move from the validation to validation and finally to a proposition. And type inference is, of course, a form of natural deduction, and that's provide us a system to reason from assumptions in programs. And the idea of this is called propositions as types. So basically, previous research back in 2015 found that types in programming is isomorphic to propositions in logic. So we have a function type that maps type A to B that equals equivalent to a proposition that inference from a statement A to a statement B. This is way back to I think 1934 from Haskell Curry. So basically the central idea is that type inference is a form of natural deduction that can help us to evaluate the core structural logical reasoning ability of chain of thoughts. And below in listing 1 and figure 2 is a pair of examples. Example in our benchmark, and a reasoning tree is generated by Cloud 3.7. We can see in listing 1 on the top, we provide the assumptions that are all the dependencies for this reasoning task, and we provide the reasoning steps, which is on line 5. And we ask the language model, given the assumptions and the reasoning steps, generate a final type signature. However, there's still a missing part. Even though we have this task in listing 1, we still cannot fully understand if the large language model is doing the real reasoning or just memorizing the task from the training data, right? So that's why we also do a input or task transformation. There are many previous work focusing on transforming tasks to obtain a performance reduction on the large language models. We have semantic preserving code transformations, and we have perturbations on mathematical problems. The works are really recent. So we also do a transformation on our logical reasoning task or type inference task. So basically, we normalize all the binary names to lowercase letter f with a number, and we normalize all the types that contains natural language. For example, in this case, integer or boolean or string or characters. We normalize them to a meaningless type symbol like T1, capital letter T1, T2, and so on. In this way, we can still prove the tasks are equivalent while removing all the natural language elements from the task to trigger real structural reasoning from the large language models. And below in listing 2 and figure 3 is a pair of examples that's the same task from the previous slide, but has the natural language removed. And now we have the other background. I will go over the design of benchmark F, TF bench. Sorry. So for constructing the benchmark, we use the Haskell prelude for 4 reasons. First, Haskell is a language that implements a formal detective type system, which namely system F. And in Haskell, the type signature is concise and can be decoupled from the function body. So, for example, in listing 3, on line 1 is the type signature, and on line 2 and 3 are the reason steps or the inference steps, the main implementation. So we can put line 1 after line 2 and line 3 or elsewhere. That's what we mean by decouple from the function body. So they're not together. And third, in Haskell, type equivalence is formally verifiable. Even if the signature only, we don't need the function body to prove the equivalence of types. And if you consider all the languages that satisfy 1, 2, and 3, Haskell is the most popular language in this case. And after we construct all the tasks, we then formally remove all the natural language from the task. So as I briefly mentioned before, we have 3 types of rewriting operators. The first one is kind of the most important one is the NL type rewrite. So basically, we remove all the natural language types to a meaningless capital letter T with the number following. We also rewrite all the type variables for polymorphism into lowercase t with the number following. And we also rewrite all the blendings, which indicates the variables and functions and the operators into a lowercase f, 1 and 2 and 3 and 4. And to verify that our alpha rewrite operators are semantic preserving, we prove that all three rewrite operators are commutative and associative under computation. And the transform tasks are all alpha equivalent to the original tasks. And in our benchmark, it's a small benchmark. We have 188 tasks that's purely for evaluation. So we don't have training or others. It's a pure evaluation benchmark, and about 26-27% are monomorphic functions, meaning that they can only be instantiated as one type. And about 32% are parametric polymorphism, and about 41% are ad hoc polymorphism. And we have two variants of the benchmark, TF bench and the TF bench pure. The pure version is the NL-free version of TF bench. And after constructing all the parts of the benchmark, we go to evaluation methodology. And figure 5 is the mean pipeline of how do we evaluate tasks in TF bench. So first, we use the ground truth type signature to add all the definitions of new types. So after rewriting the benchmark, some of the types that are built in to the prelude or the compiler that are no longer there because they are rewritten. So in this case, we add new definitions for the new types. And second, we prompt the large language model with a task to generate a new type signature. That's below here. And after that, we don't do direct string comparison of the type signatures. We construct a proof using the ground truth and the generate signatures. And if the proof compiles, we can formally prove that the two signatures are equivalent. And that gives us the sense of accuracy in this benchmark. And afterwards, as the final step, we also do an analysis of what errors are made during the logical inference. Okay, let's go to evaluations. Right. So basically, we ask three questions. First is what is the performance gap of large language models on the two versions of benchmark? So with and without the natural language information, what's the impact on reasoning? And second, how effective is test and compute of large language models? And third, how does fine tuning on mathematics or programs improve reasoning? So the first question, we provide a short table on the slides, but you can find a much longer or complete results on all the modern models on our paper. So for the first research question, we evaluate the accuracy of the models on the base version of the benchmark and on the pure version of the benchmark. And with these two scores, we can calculate a reasoning robustness score, which is just the accuracy pure over accuracy. And we can see in our case, at the time of our research, those are the most powerful models that we have access to. We found that on the base version, GPT-03 mini is the best performer, even better than GPT-03 for some reason we don't know. But if it comes to on the pure version of the benchmark, GPTOC outperforms the mini version by a large amount on the robustness. And we can also see that in this task, we can see that Cloud 3.7 Sonnet is the second in the accuracy and robustness, and the first in pure accuracy. So this indicates that you can rely more on the cloud models for like reasoning about code. And for the second question, how effective is the reasoning or test and compute? For this experiment, we select the models that we can manually control the reasoning by turning them on or off. We evaluate 3 models. Well, by that time, we only have control for these 3 models. So basically, Q1 235B, and we serve the model with FP8. And we have Cloud 3.7 Sonnet and Gemini 2.5 Flash. That time is the preview version, but that's the only 3 model we can manually control the test and compute. And we can find that not all reasoning are similarly effective. Right? We compute the effectiveness of the reasoning effectiveness by the equation below. I think. Yeah, that should be the equation 2 on the paper. So basically, we measure the improvements on the pure version over the improvements on base version. And we can see that if this score, the reasoning effective score, is close to 1, that means that the reasoning is not really doing a thing, right? The improvements by turning on reasoning on pure logical benchmark and contaminated benchmark is basically the same. So that indicates the reasoning is not very effective. And if the score is high, like for Gemini, it indicates that the reasoning is really effective. It improves a lot on the pure logical benchmark over the contaminated or already memorized benchmark. And finally, we also evaluate the effect of fine tuning on other training corpus, right? So for this experiments, we found the base model, and there are 2 variants. One is the cold version, one is the math version, right? And we can compare. Here we have Mistral and Q1-2. And one really interesting observation is that if you fine tune or continue train your model on cold corpus to produce a colder version, sometimes the improvements are negative or 0. And for some reason, if you train the model on code, the accuracy on the base version is the improvement of accuracy on the base version is always higher than on the pure version, meaning that it's overfitting to the natural language elements in the code instead of reasoning about the structure and logic behind the code. However, if you find the math version of the same base model, you can see that the improvements on the pure version is higher. Well, for the 3 models we evaluate, it's always higher than on the base version, which indicates a better structural reasoning ability after training on math. So basically, that's a summarization of my explanation of the previous slide. The observation is that fine tuning on math might enhance the model's reasoning ability, which also translate effectively to programming tasks or code-related tasks. And yeah, that's all the content I have. Yeah, thank you for listening.
Thank you for the talk. Maybe in terms of like questions, perhaps I'll direct to the audience first, and otherwise, uh, if there's none, then I can also ask some questions.
Sure.
One note: there's probably one question slot for the first session. But otherwise, we can also encourage others to kind of post their questions on Slack later on, where we can have more asynchronous Q&A later on as well. Anyways, we have one question slot.
I'm not sure if I see any, so maybe I can ask a question.
Sure, please.
So do you see like any correlation between like the improvement in like TF pure, let's say compared to like generic programming scenario? Like I don't know, like Cbench or anything that's like outside programming itself. Like and then another is that like because here I'm curious since that like the performance of like the math reasoning is better than like code. Is it just because there is no like a proper uh chain of thought like reasoning yet that are available in like on like fine-tuning data set in code? Or is it necessary because of like the structure of math that are easier to do like chain of thought in a sense?
Um, yeah, so the question can be answered from two perspectives. First, you are absolutely correct. I think the current training pipeline and training data for math elites better reading steps than just training from all the source code on GitHub. And second, it's not necessarily that the math models have better performance than the coding models. It's just the math models, the improvement ratio on the pure version is higher than the ratio on for the code versions. So you can see that the delta pure is consistently higher than the delta base. But for coding models, sometimes the delta pure is negative. Sometimes the delta base is negative too.
I see. But in a sense that like the math model would be better than like the coder, right? At least based on what I see in terms of like the overall performance or
Well, if you look at the same model size, for example, for Qwen, 7B, Qwen 7B achieves a higher accuracy for the coder version.
sorry. I guess like I compare with the Mistral since like the Quen it is Quen 2 and 2.5, so it's maybe different.
Right. So yeah, that's different for different base models, but based on our limited empirical data, we don't have a way to draw this conclusion. So we can just say that we observe that the percent or the ratio of improvements is different. And
Okay.
for correlation analysis, we did not do a correlation analysis between this benchmark and other reasoning or mathematical reasoning benchmarks, but we did a correlation analysis between this benchmark and LabCode bench, and we see a kind of strong correlation linearly.
I see. Thank you.
No problem.
So thanks a lot for both speakers for the great talks. I really enjoyed your talks actually, and these are really nice kind of instructions on respective domains of research. So And the session has been recorded and will be put on YouTube after editing out the irrelevant parts, I would say. You can opt out at any point if you wish. Yeah, so I wish to thank the speakers again for making a great session again. And with this, we move on to the next session, which is also related